the ways we can generate keys, and we've seen that two major ways. You can either generate a key using a random number generator, or you can generate a key using a password. So, when you generate the key using password, there are two options. Either you generate the key without a salt, or you can generate it with salt. Now, without salt, what was the limitation? What was the issue? No, without salt, you regenerate the same key every time, and this is not safe. This can be attacked. In what way it can be attacked? What is a famous attack for this generating a key from the same password? This is the passphrase. By the way, secret is not a keyword. It could be anything. It could be password. Could be Doha Qatar 2022. Could be whatever. So here, if I do no salt, have a look at this. Same key get generated, and this is not good. Why is it not good? Sorry? Yes, so this is vulnerable to dictionary attacks. Dictionary attacks is an attacker will bring a list of kind of possible passwords, especially these days, very easy to get from these hacked famous databases. You get millions of passwords. You can just try some of them, generate the key based on these passwords, and try the key. So what is the solution to this? How can we avoid this? How can we avoid generating the same key using based on the same password? By using salt. So what is salt? So it's a random number that gets concatenated with the password, and then based on these two, not only the password that is static, based also on this salt, which is random, we concatenate the two, and then based on this the result of this concatenation, we generate the key. Now, is the salt secret? It is not secret. The salt, you send it to the ciphertext. When you send the recipient, when they receive the ciphertext will have two parts. One is the salt, and the other one is the actual ciphertext they need to decrypt. Why do we need to send them the salt? So they can generate the same key. Otherwise, they will not be able to generate the same key. So let's see so you see the difference here? If I say no salt, can you see when I generate the key, I get exactly the same key. Now, as soon as I remove this no salt, so two things happen. There is a random number get generated. This is basically the salt, and this is the actual key. Have a look at this. When I run it again, I get a different key, totally different, and of course, different salt. Now, the recipients, for them to generate, if I use this key to encrypt, the recipients need to receive this salt also to be able to decrypt. So the way they will generate their key is that they will do this command, plus they'll have to provide the salt. And here's the salt, so if I take this one, you see, when I use the same salt, I get the same key. So the recipients will have to use the salt to generate the same key for them to be able to decrypt. And this makes the communication much more secure, because I can use different salt for different messages. Every message I send you, I can use different salt, and this hacker will not be able to work out the key. Even if they manage to do a brute force attack or a dictionary attack, there is no way they can work out the key. The key will be every time, the key will be different. Every session, every communication session I have with the recipients, I can make the key different by using different salts. So I hope this one is clear. So this is the first thing we need to do encryption and decryption of messages. We have to agree on a key. Yeah. Now we will see, of course, more advanced ways to exchange the key without actually exchanging the key, establishing a session key without actually exchanging the key. One way is this. One way, what is the secrecy here? What do we keep secret here? Just the passphrase, the password. Yeah, and the key will get generated every time. So once we generate the key, what we do is we go ahead and you encrypt and decrypt. Now, when we encrypt and decrypt, there are so many ciphers that we choose from. That's why we need to study them and we need to make an informed choice. So we have, I'm showing you here a couple of them that we have already seen, and introduce new ones that I will be discussing today. So now what's happened here, there are two ways I can use the encryption and decryption. Either I can supply the key directly, the key that I have generated before, I can supply it here. So have a look at this. So what I'm doing, I copy this. First of all, I show you the ciphertext, the plain text. Here is the plain text. Now this is I'm asking for this plain text to be encrypted using RC4. Remember RC4 cipher? And here is the key I want to use. I want the output to be encoded in base 64. This is the input file, and this is the output file. It went ahead and did it, and then here is the ciphertext. Here is the ciphertext. So part of it, maybe this first part is the salt. No, here, sorry, there is no salt, nothing. Here's just the key. Here I provide the key explicitly. Now if I want to decrypt, of course I must use exactly the same key. Here is the decryption. Okay, here. So it goes ahead and decrypts. This is how I decrypt, by passing this minus deep kind of parameter, and then flag, and then here is my key, and then I go ahead and decrypt the ciphertext and write the output to this file. Okay, so if I do and I get back the exact same plain text. Now if I change the key, even with, of course, whatever, one letter, of course, it will not work. It gives me some weird, this is not my plain text, because the key is different. Okay, so I will only be able to decrypt it using the same key. This is one way of using the OpenSSL. I provide my own key. Another way of using it, I provide just a secret. Instead of using K, you see the difference here? The difference here, K is uppercase. I provide the whole key. Here, K is lowercase. I am providing here the password or the passphrase. I want to add one more. Let me add one more flag here. No problem. Let me put it here. I'll add one more flag, which is -P, so it can show me the key that will get generated. It went ahead and did the encryption, and this one is the actual key that was used. You generate the key first, generate the salt. Which one it will be sent to the recipient? Both the ciphertext and the salt. In fact, OpenSSL will combine both. So the recipient, let me just remove this -A. Remember what this -A does? base 64 encoding. Remember, base 64 encoding. So let me run this again. And then I'll do cat save ciphertext. You see here, you can see the first word is called salted. Somehow it's included in the salt random number. So the ciphertext will have both the salt and the actual ciphertext. What the salt will be used for? It will be used by the recipient to generate the key. For the recipient to generate the key, what they need? Two things: the password and the salt. Then once they generate the key, what can you do with the key? They can use it to decrypt the actual message. In OpenSSL, all I do here, here it is. Because I didn't do base 64 encoding, so I have to remove this -a. And if you look here carefully, I did here the decryption, and the actual key that was used by decryption is exactly the same one that was used by encryption. Did I exchange the key with the recipient? No. I didn't exchange the key with the recipient. We agree. What is the agreement between me and the recipient? Just a password. That's it. The salt is passed in clear text with the ciphertext. There is no password. The salt is not secret. The salt is public. It can be sent on clear text. So this is basically the idea in concrete way, in practice, how we use cryptography. So RC4 is just one of the algorithms. There are many other algorithms. One of them happens to be DES, Data Encryption Standard, and that's what we will be discussing today. But just exactly the same idea. The only thing I do different here is that I ask OpenSSL to use a different algorithm. In this case, I'm asking to do encryption using DS and exactly the same idea. I give it a password, it will generate the key and generate a salt. Let me put -p. Generate a key, a salt, and IV. I will explain what this IV means later on. It's called initialization vector. Don't worry about it. RC4 does not use it. DES generate three things. The salt will be used by the recipient to regenerate the key, and the IV initialization vector, I will explain what it means later on. And decryption, exactly the same, except I pass this extra flag -d to do the decryption. So I hope it is clear. You can also use other DS, although it is very robust and very has been used for a long time, but since 2000 it has been broken. No longer recommended. Don't use it. The key can be basically broken by brute force. So it was replaced by this triple DAS, or the most commonly used one today is this AES that we will be covering maybe next session. So exactly the same commands as you see here. The only thing different is instead of using DAS, I will use DAS 3. And then if I want to use AES, exactly the same, I use AES. Now AES comes with different keys. You can use AES with 128 bits, or 192 bits, or 256 bits. While DAS, what is the size of the key? 64 bits. And that's why it is vulnerable, because the key is short. So I will not go through this. It's exactly the same concept. Here I'm using these examples just as a motivation for us to highlight the need to understand these algorithms to be able to choose the right ones and to be aware of their capabilities and limitations. There are other ones also that are not as famous. One of them, for example, called blowfish. So what happens is, if you remember, I told you DS was was invented by IBM with assistance and input from NSA, and it was developed behind closed doors. It was secret, and then it became standard. Now, AES is totally different. AES, the NEST, which is the National Institute of Standards, it issued a request for all cryptographs of the world to come up with ciphers and to go into some kind of competition. So there was like an open call for people to submit their ideas, and then 15 were shortlisted, then studied for 1 year, then 4 were shortlisted, and then studied for another year or 2, and then finally one of them was selected. Now the other four that were shortlisted with AES are also known to be very, very secure. So one of them happens to be Blowfish. So if you hear this, Blowfish is just another kind of competitor of AES, but by far AES is the most widely used cipher today, and it's unbreakable. And we will see that, we will discuss it further next time. So I hope you kind of get the idea. And here you can see here, when even in the beginning when I showed you the need for understanding these ciphers, if I go ahead and do OpenSSL, and do encrypt-help, you can see there are so many ciphers. So, and even DES, there are many modes. There is DES CVC, DES CFB, DES ECV. What this all means, we have to, I'm just trying to highlight the need to really understand. It's not just using this tool. You can, of course, use it, but you need to understand what this all means. That's why we will be spending some time not only covering these algorithms in high level, we will try to open the box and see how the magic works from inside. Before I do this, this is the last thing I want to introduce as a motivation, is all these ciphers that we have discussed so far, RC4, DAS, AES, Blowfish, all of them are symmetric cryptographic algorithms. Now, what do we mean by symmetric? Same key on both sides, and we have seen it. Now, the other type of cryptographic ciphers, they call themselves asymmetric encryption. You will see, of course, the details later. But what is the key idea here of asymmetric encryption? Two keys, private key and public key. Public key means everybody knows it. Private key, only the owner knows it. So the first thing you do to do asymmetric encryption, similar to what we did for symmetric, you generate the key to do encryption and decryption. In here, in asymmetric encryption, you create two keys, private and public. And here, the keys are much larger. The keys are much larger, which means asymmetric encryption, in terms of performance, if we compare it with symmetric, it's much, much slower. So usually in practice we use both. We use asymmetric encryption to just establish a session key. We exchange a key for a particular session using asymmetric encryption. And then once we establish a key, then we use symmetric encryption. So we use both because symmetric is much, much faster. We will see this in practice. You use both at the same time. You use asymmetric initially to establish the session key, and then after that, from that point onward, you switch to symmetric encryption to make it faster. So the first step, as we've seen in symmetric, is we need to generate the key. So how do we generate the key? This is one way of doing it. In here, you cannot use random number generators. We will see a bit the math behind it in a lightweight. There's a lot of complex math behind. But here, the private key and public key are mathematically related. They are not really random numbers. So you generate the key, the private key, and then you generate the public key based on that private key. And these keys kind of go together. If you encrypt with public, you can decrypt with private and vice versa. If you encrypt with private, you can decrypt with the public. So here is how you generate the private key. So I go ahead here. So I'm asking the algorithms, for one of the algorithms of asymmetric cryptography is called RSA. We will see this later on. So what I'm asking here, asking RSA, please create for me a key with 2048 bits. And this is a small key, by the way. It can go much bigger. So here is the idea. So it goes ahead and generates the key, and the key now is stored in this file called private key. Let's have a look. Here is the private key. It's a huge number. Then once I generate this private key, this is top secret. Like private key of QU, it's top secret key, cannot be revealed to anyone. For Microsoft or for Google or for these are top secret keys. It cannot be revealed to anyone. Now, based on this private key, we can go ahead and generate the public key that we can make available to anyone. So it went ahead and generated the public key. Now, if I do here, oh, sorry. This is the public key related to this private key. Now, this public key is public. Anybody can get hold of this key. By the way, if there are tools out there, I can, for example, later we'll see this in much more details. But if I can use this as a small example. I can use this command. I can use this command, OpenSSL client, and I'm asking GitHub, please give me your public key. I can ask any website to give me the public key. So public key is something well known. And then it will go ahead and ask, it's now going to GitHub and getting me the public key. At the end of the day, I will get some key like this. And I can use it. Let's say if I want to send something secret to GitHub, I can encrypt it using their public key, and they can, this is their public key. Yeah. And I can send it off, and they can, it's only them they can decrypt it, nobody else, because they have the private key. So I just want to show you this. Then what I can do once I have the public key and the private key, let's say I want to send something secure, all I need to do is, this is how I encrypt. So I'm saying here, use RSA, which is an asymmetric cipher algorithm, and go ahead and encrypt for me using the public key, encrypt this plain text and write it into this ciphertext file. So it goes ahead and generate the ciphertext. Here is my ciphertext. This is the ciphertext. And then if I want to decrypt it, I have to use the private key. The only way to decrypt this message is using the private key. So this cipher could be generated by anyone in the world because the public key is known. Now, once the recipient gets it, then they will use their private key to decrypt it. And this is the idea of asymmetric cryptography. If I do here cat, you see here, it was decrypted. And here, what is the advantage here of this asymmetric cryptography? What is the key advantage? There's no need to exchange the key. Thank you very much. No need for key exchange. The public key is public, known, and the private, and basically it works both ways. Now, if I want to ensure confidentiality, all I do, I encrypt using the public key, send it off, and the recipient will be able to only the recipient having the private key will be able to decrypt it. The other way around, the sender could encrypt using their private key, and anybody in the world can decrypt using their public key. So what are we trying to achieve here? Is it confidentiality? No, not really confidentiality, because anyone can decrypt it. What are we trying to achieve using this encrypting using private key and decrypting using the public key?
Ensure that this is the organization that sent.
Yes, it's authenticity of the message, that this message is coming from a particular entity. This is establishing the authenticity of the message. So for example, I gave you before the example, if QU wants to send your transcript to another university where you apply for your master or PhD, they can take your transcript, encrypt it using QU private key, and then send it off to Harvard or whatever university you will go to do your PhD. And then what the recipients will do? They will decrypt it using QU public key. And what that gives them, what confidence it gives them? That definitely this transcript is coming from QU and nobody else. No one else can have this, can really, this message cannot come from anywhere else because the private key is only owned by, in this case, by QU. You get the idea? So this is concretely what is symmetric and asymmetric. And all this discussion we have been doing last session and now is just to motivate you and to see this in practice so we can open the box and see what is behind. Last thing I want to discuss before I go into the opening the box is I go here and say message signing. So cryptography usually it gives us this assurance or protection of it gives us the protection of what's protection it gives us? Confidentiality, yes. And if we use asymmetric, it gives us confidentiality plus message authenticity, yes. Now it still does not give us integrity. The message can be still changed along the way. It can change. What I mean here, let's try this. Let me just take back to a simple algorithm. Let us take this one. So I'm using now, and here is my cipher. Here's my ciphertext. Now what I can do here, I can go ahead and change this one to D. Change it. This is what integrity means. Somebody intercepts the message and they can tamper. This is the term we use, tamper with the message or change the message. So now I save it and I'll try to decrypt. So decryption, once ahead, there is no error, there is no warning, nothing. So I am not protected. So here's my cat. So you see here, it did the decryption, except this one became, instead of the lazy dog, it became easy dog, something like this. You see, there is no protection against integrity attack. So the message can be tampered with. There is no protection. It's protecting against, it's protecting our message against like attacks on confidentiality, but not on integrity. So encryption ensures confidentiality, but the message can still be changed along the channel. So how can we protect against integrity attacks or preserve the integrity of our message? How can we detect that the message has changed along the way and this message is no longer valid, has been changed? How can we do this? Encryption will not help. Yes, checksum, okay. So basically, in here, another family of technology which is related to cryptography is message signing. So what I do, I sign the message. I generate a digital signature. And basically, when I send the message with the message I send, a digital signature. And then the recipients, what they can do, they can take the message, generate a signature based on the message, and then they match the signatures. If they match, then the message is originally, it was not changed along the way. Otherwise, if a different signature is generated, then the message has been tampered with. So let me show you a small example here. So one way to do it, simple way to do it, is doing hashing. And that's what we will discuss later. What I will be doing here, so here is my original message. So here's my original message. Okay. Now what I do, I send this message to the recipient. Before I send it, I can generate a hash. There are many algorithms to generate hash based on message. One of them is MD5. So this will generate this hash. This is the hash for this original file, yes? So you see there it ends with F1C. Now if I go to the same file and then just remove this dot and then save it. So the recipients of this message, they're supposed to do the hashing. So they know this is public, this piece of information is known to the recipient. If they do the hash, you see here they get completely different hash value, which means the file has changed since the sender has sent it. So a very simple mechanism to ensure integrity. The recipient of the message, they do hashing when they receive it, and if the hash does not match the hash that the sender has provided, it means the message has been changed along the way. So a very simple mechanism. Now, more realistic and more sophisticated mechanism, not only I want to make sure the message has not changed along the channel, I also want to make sure that the message is really coming from the recipient, not from somewhere else, not from someone else. So to do that, what I can do, the sender can generate a digital signature, sign this message using their private key, and then the recipient will verify that signature, that this message really comes from this recipient, this sender. So to do so, to generate a digital signature, so digital signature ensures two things. It ensures that the message has not changed, and the second thing, it ensures that the message is coming from a particular entity. So I go ahead and sign the message using digital signature. Here is the digital signature that was created. Okay. So this is not encryption. This is the actual digital signature. And then the recipient, when the recipient receives the message, whether it's encrypted or not encrypted, it doesn't matter. What they can do is they can verify that the message has not changed, and the message, so in here I'm saying sign, and in here I'm saying verify. So I sign using the private key and verify using the public key. Sign means the sender signs the message, generates a signature, and then the recipient will verify that that message has not been changed and it's coming from the original recipient, not from someone else, not from somebody else. And it says here the verification is okay. So what I want to say here, encryption is, we use it to protect the confidentiality, but it's not enough. You still need to do digital signature to ensure integrity and to ensure message authenticity. Now, in practice, you can do both at the same time. And this is called authenticated encryption. Authenticated encryption. You are protecting three things at the same time. Three things at the same time. You are protecting confidentiality, integrity, and authenticity. That the message is coming from the original recipient, not from some kind of fake recipient, fake sender. Okay, so here is how you do it. So, and to do this, typically you use asymmetric cryptography. So in here, what I'm saying here, go ahead and encrypt using RSA. Here is my private key. Here is the plain text generates the ciphertext. This ciphertext has both. It can ensure the three things: the confidentiality, integrity, and authenticity. Then here is this signed text will have the ciphertext plus the signature all together. And then when the recipient gets it, all they do, they can go ahead and verify the signature, at the same time decrypt the message. So here, when I say verify, it decrypts the message and gives it to me. Now, if there is anybody tries to attempt, let's see, like this is the ciphertext. No, in this case, I called it signed text. Yep, this is the signed text, scary stuff. If I try to change, this is tampering with the message, trying to change anything in the message. If it was plain just encryption, then it will be decrypted, no problem. Of course, the plain text that we get will be a little bit different than the original, but there is no way I know, especially programmatically, that the message has changed. But now, using signature plus encryption at the same time, I can detect if this message has changed. If it's changed, I throw an error and I cannot decrypt this message anymore because it has been changed. So if I try now to verify, it says here, RSA operation error. Public key decrypt. Anyway, what it's trying to say, this message is not the original message that was sent by the sender. So it detects tampering with the message. So I hope it's clear end to end. Of course, we will get into the details. I just wanted to, in this session, I want to give you like an end-to-end view, practical view of asymmetric encryption for protecting confidentiality, and the problem of the headache of exchanging the key. And then we looked at asymmetric encryption, where we don't need to change the key. We use two keys, private and public. And then both of them, they don't really ensure, they just ensure confidentiality, but not integrity and authenticity. And then we looked at, to ensure integrity and authenticity, you need to use digital signatures. And in real life, you use both at the same time. And that's what we call authenticated encryption. It ensures three things at the same time: confidentiality, integrity, and authenticity of the message. So now that we understand the overall picture in a practical way, we want to start diving into each of the algorithms in a little bit more details. And there's a lot of magic, and even the people behind this, even in the error messages, some error messages, they kind of reveal that they are using some kind of magic. So I once tried one thing, and then it says to me something like bad magic number or something like that. Okay, let me try it. Yes. I'm trying to, this message was encrypted using DES or DAS. I'm trying to decrypt it using RC4, and it's saying bad magic number. And just to highlight that when you really start looking into this, it's really magic, because we went from the lazy dog jumped over the fox jumped over the lazy dog to this Chinese. It's really magic. So it's exciting to really open the box and see what's really going on inside. So inshallah, that's what we will be doing next time. So I will be covering just to give you the roadmap, I'll be covering DES, hopefully next session, and the session after we will cover AES. And then we start looking into asymmetric cryptography, hashing, digital signatures. And then we will wrap up this part of the course. Okay, thank you very much, and see you next time.